very last Go Board tutorial. Everything we've been learning so far has been building towards this tutorial, and today we're going to be describing how we can get the game Pong to work on the Nandland Go Board. That's right, with the Go Board you'll be able to recreate the fast-paced action from the 70s. So I hope that the tutorials at this point have put you on a good footing for your FPGA journeys. I hope that you found working with the Go Board to be fun and easy. That's been the main goal. Please let me know, post in the comments section of the YouTube videos if you had any problems, if you're still confused about anything. I do want that feedback so I can improve my videos and answer any questions that are still out there. I do plan on making more videos in the future, but probably the quantity of the videos that I make depends on how well received the Go Board is in general. If people continue to purchase it, it'll be more motivating. So tell your friends, and I will post more videos if people buy the Go Board. So this will fulfill, as far as I'm concerned, the original goals I had for the Kickstarter, which was just to not only sell a board, but also provide a lot of support for that particular board. I find too many other boards are just, someone makes it, throws it up online, and then it dies. I don't want that to happen with the Go Board, with Nandland, so I'll continue to make videos, but again, it's more motivating when people are actually out there purchasing the board. So spread the news, tell your friends, tell your professors, whatever you can do. Let's get started talking about Pong. This is what Pong looks like, very advanced stuff. Each player has a paddle represented by a rectangle. So player 1 has their paddle on the left, player 2's paddle is on the right, and there's a ball represented by a square that is bouncing between player 1 and player 2's paddle. On the Go Board, I want to control player 1 with button switch 1 and switch 2. So pushing down switch 1 makes player 1's paddle go up. Pushing down switch 2 makes player 1's paddle go down. And then player 2's paddle is controlled by switch 3 and switch 4. So if you want to play against somebody, I played against myself, but if you want to play against somebody else, you got to be pretty comfortable with them because it's relatively tight to get 4 fingers on those 4 buttons, but you can make it work. So the way that this game works, you play up to 9, basically, and when the first person who gets to 9 wins. So here's the way that I chose to implement the Go Board. And I'm going to talk through my solution and how it works. I do expect that you've at least done the intro to VGA tutorial so you understand how VGA works. That was the previous project. If you haven't checked that out, definitely go check that out first. That's important knowledge. And this project builds on that one. So everything you see here in green on this block diagram is a direct port of code that we've already used. So the UART receiver we've done, the sync pulse generator came from the previous project, sync to count came from the previous project, the debouncers came from a project a long time ago, and the VGA sync port module modifies the horizontal and vertical sync to fit in the front and back porch was the previous project as well. So really all we're adding in is this Pong top logic, P1 paddle, P2 paddle, which are actually the same exact module, just instantiated twice, and the ball control module and a little bit of logic around it. So it's not too bad, but it is worth talking through how it all fits together. So I'm just going to talk briefly about each one of these blocks, I suppose, would be the best way to do it. So the P1 paddle block, P1 and P2 paddle are responsible for keeping track of where each one keeps track of one paddle. So P1 paddle, let's talk about that. P1 paddle keeps track of where the paddle is on the screen. Now, the way that the monitor is actually indexed is 640 columns by 480 rows, for like the previous project worked. But the question is, how can you actually treat the game board? Do you need the game board to be a 640 by 480 game board? Do you need every single pixel to be represented? If so, it's just a lot more data to keep track of. So I said, nah, let's keep track of less data. So let's make, rather than making it a full 640 by 480, if you divide 640 by 32, 640 divided by 16. Let's do that. And 480 divided by 16. So you divide 640 and 480 by 16, you get 40 by 30. That's actually a much better size for a Pong game. So now instead of being 640 wide, it's going to be 40 locations wide and 30 locations tall. So the width of a paddle is just going to be 30 pixels. And I think that, 32 pixels. And the width of the ball is 32 pixels, the height of the ball is 32 pixels, and the length of the paddle is a little bit bigger. You can work with different sizes to figure out how long the paddle should be. It's harder if the paddle is shorter, it's easier if the paddle's bigger. But what that does is it gives you less space to keep track of, it keeps your counters a little bit smaller, and it's just an easier way to deal with things. And it makes your paddles the right dimensions without having to do too much work. So that's what I did. I used a 40 by 30 game board. Each paddle, I think I said the height was 6 units of the game board high and 1 unit of the game board wide. The ball is 1 by 1. And like I was hinting at before in this block diagram, P1 paddle just controls where the player 1's paddle is vertically on the screen. You know where it is horizontally at all times. It's always locked on this column, which I believe is just going to be column 0. Player 2's paddle is going to be locked always on column, if it's 40 wide, it's going to be locked on the very last column, which is going to be column 39 if you're indexing from 0 to 39. So player 1's paddle in X is at 0, player 2's paddle at X is at 39. At Y, it does move up and down, so you need to keep track of where the paddle is in the Y location. Okay? And when the image is being drawn, it's being drawn top left to bottom right, when it gets to that paddle location, it's just going to output a single pulse that says, yep, the paddle's here, draw something at this particular pixel location. When the buttons get pushed, the paddles move, and you do need to check to make sure that the paddle doesn't just slide off the screen, off the top or off the bottom of the screen, which I did have that problem when I first designed it. I kept hitting the down arrow, and the paddle just kept moving all the way down the screen. You do need to check for boundary conditions. So that's pretty much it for the paddles. For the ball itself, the ball can move only diagonally, but it can be moving in 4 different diagonal ways. It can be moving diagonally up and to the right, up and to the left, down and to the left, down and to the right. So you need to keep track of which direction it's moving. And the way to keep track of which direction it's moving is where it was previously. So if it was over here and it was moving in this direction, you're going to keep drawing it in that direction until it hits something. What can it hit? It can either hit the side of the game board or it can hit a paddle. And that's pretty much it. So if that happens, then you just change the direction that it's bouncing in and you make it bounce the other way. You need to know if it hits, does it get hit from the side? Does it get hit from the top? Does it get hit from the bottom or the other side? And the way Pong Top works is that P1 paddle, P2 paddle, and ball control each have an output, just a single output that says something is at this particular row call index. If something is at that row call index, then I just say draw something on that pixel. This OR gate here that I represented with this giant OR gate doesn't really care what it's drawing. It doesn't know, oh, this is a paddle that I'm drawing or this is a ball that I'm drawing. It's just drawing something on the screen that's not black. In this case, it's just going to be white. So it just does an OR of all 3 of these, and if any one of these 3 tells the drawer to draw at that particular location, it'll output a high at that location, and that gets sent to the VGA display. That's basically it for Pong. There are more things you can do. For example, keep score on the 7-segment displays. That's a fun one. I do keep score inside, but I don't actually make it available to the user, so it would be nice to take the score that's currently the score of the game and shove it out to the 7-segment display on the Go board. So maybe player 1 is on the left 7-segment, player 2 is on the right 7-segment, for example. My Pong implementation is white on black, kind of boring. You can change colors. Try that out. You might be able to add UART control, so dynamically change colors. Maybe hit 1 through 6 and change the colors of the game board to whatever you like. The game board can actually get bigger using block RAM, which is a concept that we haven't touched on yet. But I probably am going to make a video about block RAM and how it works inside the FPGA at some point. and whatever else you can think of to make Pong more fun. I recommend spending some time with this and really getting to tweak your code and get familiar with how you can affect the data going out to a VGA monitor. So with that, I'm going to get started showing off the Veralog solution first. If you want to skip ahead to the VHDL solution, feel free to do that. This particular project doesn't have a simulation for it, which was lazy of me. But it's kind of one of those ones that I felt confident enough and I could see the results of what I was hitting that I didn't feel a simulation was necessary. Shame on me. Anyway, let's get started with Verilog. Let's talk through the Verilog solution now. Now, normally when I go through the code, I tend to do a bottom-up explanation of the code where I start at the lowest level modules and work my way up to the top. In this one, I'm actually going to start at the top and work my way down. So I'm going to crack open Project 10 Pong Top and just show you what this one looks like. This is the signals coming in from the Go board here. I have the UART RX being instantiated. I have the VGA sync pulses being instantiated. And the sole purpose of this is just to generate the H sync and the V sync at the appropriate window for the VGA. Debounce 4 switches so that we get some nice clean switch inputs. Here's Pong Top being instantiated. And then the output of Pong Top is just the H sync, the V sync, red, green, blue video data, and then that goes into the VGA sync porch, which modifies the horizontal and vertical syncs to get the ones going to the VGA monitor. And we just peel off each individual bit of the colors and send it out the VGA connector. Alright, so the only thing that's new here is Pong Top, so I'm going to go there next. There it is. And we do need to know a few things about the Pong setup. So we need to know the total number of calls in rows, total number of active calls in rows, and here's where I define the game width, and the game height, which I said is 40 by 30. The game is up to 9. The paddle height is 6 pixels, quote unquote, where pixels are in this height of 30. So it's 1/5 of the total image is going to be the paddle. You can change that to whatever you like. And then this is the call index of where player 1's paddle exists in the column dimension. So player 1 exists at column 0, player 2 exists at game width -1, which is going to be at index number 39. So player 1's paddle is going to be on the far left of the screen, player 2's paddle is going to be on the far right of the screen. And just looking at the module input and output, we have H-sync and V-sync coming in. We have some game start coming in, which is just going to be the UART, which tells the game to get going. We have the player 1, player 2 controls, and then the video data being driven. That's it. I should mention that the game start that I chose to use was just any data valid pulse on the UART. It kicks off the game. You can do it a different way. I didn't have... it'd be nice to have one extra button on the Go board, but I don't. So, had to use something to kick the game off. So that's what I did. And let's see. Created a little state machine here with some enumerated types. And okay, so we have the sync to count module, which I did show in the previous project, where we just turn the H-sync into a call and a row counter that just allows us to know where we are physically in the frame. And when I was talking previously about how we're going to be dividing by 16, that happens right here. And I should talk through these two lines because this is important to know. When you're dividing or multiplying inside of an FPGA, if you divide or multiply by base 2, you can do that really, really easy. Any number that is a power of 2. So if you divide or multiply by 2, 4, 8, 16, 32, 64, 128, 256, 5, 12, 10, 24, etc., you can do that just by dropping or adding bits. So in this case, we're dividing by 16. We're going to be dropping the 3 least significant bits. We're going to be dropping 3 down to 0. If you drop 3 down to 0, you divide it by 16. If you add 3 bits or 4 bits on the least significant bits, just tie them off to 0, you'll multiply your number by 16. So very handy trick. If you need to divide by 15, yeah, that gets harder. 15, doing division inside of an FPGA is not, it's not like C where you can just say like 5 divided by 3 and just have it calculate something. A little bit more complicated than that. So let's see. Pong paddle control, you have your 2 paddles here. This is paddle for player 1, paddle for player 2. The output, okay, so I should talk about the input are the column counter, div meaning the divided column counter, the divided row counter, the paddle up, paddle down control, and this is the debounce paddle up and paddle down. So this is nice stable signal. And then the output of this is, the main output is just this O draw paddle, which says at this row and column, this row, draw the paddle for player 1 at that particular location. Additionally, I had to pass out where the paddle is physically located. So this is the in Y, where is player 1's paddle in Y. And the reason I had to pass this out to this module is because this needs to know for keeping track of where the ball, who scores on who. So if the ball crosses over and doesn't hit the paddle, then you need to change the score of the game. So I'll talk about that in a second, but I did need this information. So the only difference between these two, it's the same exact module, Pong paddle control. The only difference is this parameter here passing in the column for player 2, which is column 39, versus over here, this is column 0. Other than that, these two are exactly the same code. The ball itself, the ball is being drawn, the ball is moving when the game is active. When the game is not active, the ball is stationary in the middle of the game, waiting for you to kick off a new game. And the output of this is this draw ball signal. So it'll draw the ball at this particular row and column where the ball is located. And then it does need to pass the X and Y position of the ball to calculate the score, to figure out who scored on who. That's this state machine down here. So you basically chill and idle until game start gets hit. Someone hits the game start button, which is the data valid pulse from the UART. You go to this running state. And you stay in this running state until somebody scores. So you're running and running and running and running and waiting for something to happen. And you know somebody scores when the ball in the X position is equal to 0, and basically this is checking that it didn't hit the paddle. So if the ball is equal to 0 and there's no paddle there, meaning the player didn't get his paddle to the ball in time, then player 2 scored on player 1. Conversely, if the ball is at game width -1, which is the very end of the game board, and the paddle's not at that location, then player 1 scored. If player 1 scored and you're at the limit, game's over. If player 2 scored, you're at the limit, the game's over. Otherwise, you go back to, you increase player 1's score and you go back to the running state. So that's it for the Pong top. Let's dive into the Pong paddle control to show how, I didn't change anything, how the paddles work. Alright, so the Pong paddle control here has talked about the inputs. I do have this paddle speed. So this is the speed of the paddle movement. And what this basically means is that the larger this number gets, the more time it takes for the paddle to actually move. So I chose 50 milliseconds. So every 50 milliseconds, the paddle moves 1 board game unit. So that you can slow down or speed up the paddle draw speed. Because if you move the paddle on every single frame, then one push of the button, if you held the button down for 100 milliseconds, you'd move it, 5 units of the board game. With every 16 milliseconds, it would move once every frame. One frame is 60 hertz. 1 over 60 hertz is 16.67 milliseconds. So if you push the button down for 32 milliseconds, it would move 2 units, which is like such a quick amount of time. You push the button down, you're going to be pushing it down for at least a quarter of a second. 250 milliseconds, it would be at the bottom of the board instantly the second you push that button. So you really can only update the paddle once every so often, and that's what this paddle speed is basically doing. It says, wait 50 milliseconds before you actually update the paddle, and this just counts clocks. Again, can't keep track of time inside of an FPGA. Okay. You can't explicitly keep track of time, I should say. You can count clock cycles, which gets you time, but you can't wait for some amount of time that's not built in to any part of your synthesizable code. Okay, so the paddle count can be enabled when I just said, only allow one button to be pushed at a time. If you push both buttons, then you don't want the paddle to be moving. So this is an XOR operation, either or but not both. And when the paddle count is enabled, then we check to see, we just keep this paddle count incrementing here. Paddle count, whenever the button is held down, we're going to be incrementing this paddle count signal over and over and over and over and over again. Crude, but it works. And we only are, so that's what that's doing. This little statement here is only allowing the paddle position and Y to be updated every so often. In this case, one of the conditions is that the paddle count is equal to paddle speed. So only once out of every 1.25 million clock cycles am I actually allowing the paddle to move. Otherwise, it's just going to be incrementing this counter. This is all still running in parallel, but it's not actually updating the paddle position until this condition is true, among other things. You also check in to see that the paddle is moving upward. If it's moving upward, and we've had some time elapse, and we're not at the top, that's this condition here, then subtract 1 from the paddle location and Y. Otherwise, if the button down is being pushed and the paddle count is equal to paddle speed, so we're at the update time, and paddle Y does not equal the bottom, is what this is, then move the paddle down. And down here we just are drawing, this is just drawing the paddle. So if the current column and is equal to the player's column of the paddle in X, and the current row is basically, this is between the bottom of the paddle and the top of the paddle. If the current row is between the bottom and the top of the paddle, then we're going to draw the paddle at that row column index. Otherwise, don't draw the paddle there. That's it for the paddle control. Ball control. I find it's best to separate logically what's going on in the game. You try to put all this in one file, it's just going to be too overwhelming. So I like to separate. And the nice thing too is that you only need to write one paddle control module. So that's cool. Anyway, ball control. Same idea. We only update the ball every so often. You could have the ball updating quicker than the paddles. That would be a really hard game of Pong, so I had them update at the same speed. But you can play with that. And the ball, you do need to know where the ball was previously. So that's what this previous signal is here. If the game is not active, so if game active is equal to 0, then we're going to set up the ball to be in the middle of the board. Game width over 2, game height over 2. Additionally, you do need to set the previous value of the ball. So I said that the X previous was 1 greater, and the Y previous was 1 less. So this tells it which direction the ball is moving when it starts, and I believe it moves down and to the left when the game starts. You can move. If you change these previous values, you can make it move in different directions when the game gets started. Because down here, we do the same thing where we're incrementing the ball count by 1 every single clock cycle until the ball count gets equal to ball speed, and then we reset it back to 0. When the ball count is equal to ball speed, then we run some extra stuff, which is all this extra stuff to update the ball position. So you only do this every so often. So the very first thing, you want to register the current value into the previous value, because this is the value that's going to be updated. So this is the old value, this is the current value. And we're going to be updating the current value down here. So here are the 4 possible options. Ball X can move to the left, ball X can move to the right, ball Y can move to -1 is up towards the top, +1 is down towards the bottom. And you can look at these conditions, but basically it's trying to figure out which way the ball is moving and if it's at the edge or not. Okay? And if the current column is equal to the current ball position in X, and the current row is equal to the current height of the ball, then we're going to draw the ball at that row and column. There's only one position on the game board where the ball exists. So this one's a little bit more simple than the paddle. Otherwise, don't draw the ball because it's not there. Are we done? Is that it? I think that's it. Put everything in your Ice Cube project, build it, and let's take a look at the results. I am going to be showing the VHDL solution next, so feel free to skip over that. I'll put a link so you can skip easily. For the VHDL solution, I'm going to be talking through the code from the top down. Normally I do a bottom up, end with the top, but I'm going to start with the top and work our way down. Here we go. We have the input switches, the input UART, the input VGA. We're going to be defining the size of the frame, which we did previously. Here's the UART receiver. Here's the VGA sync pulses module. Here's where we're going to be debouncing all 4 switches. There is Pong, and there's the VGA sync porch, where we peel off each one of the bits. So just let's go into Pong top and drill down and see what Pong looks like. Alright. There is one new thing here at the top I do want to point out. Library work, use work.pong package, VHDL package files. I'm going to show you what's in this package file. It's basically a collection of, I used it to collect some constants that I defined that are going to be constants used throughout the game of Pong. So you basically can set up these constants in one location and have all of the files that use those constants just refer to this package file. Convenient way to store information that gets used by multiple files. The input signals are the H-Sync, the V-Sync, game start button. Now I don't have 5 buttons on the Go board, so I had to do something to actually kick off the game to make it go, and that's why that's what I use the UART for. So anytime you see a data valid pulse out of the UART receiver, that kicks the game off. Could do it a different way, that's the way I chose to do it. Player 1, Player 2 paddles, these are the debounced versions. The debouncer was at the higher level. And then we have the H-Sync, V-Sync outputs, as well as the red, green, blue video. Going to be creating a little state machine, so I created an enumerated type for that. And there are the call count and row count, which are going to be from the sync to count module. But there's also going to be a divided version of those signals. And what I did here is I just peeled off, so this is a 9 down to 0, so that's 10 bits. This is 5 down to 0, that's 6 bits. So what I did was I peeled off the least significant 4 bits of the column and row count. And what that does is that actually divides the column count and the row count by 16. It's a very handy way to do multiplying and dividing by any base 2 number in an FPGA. If you want to divide or multiply by 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024, etc., then all you need to do is, for dividing, drop bits, and for multiplying, add bits, or concatenate bits, I should say. So we're dividing by 16. 16, to represent 16, takes 4 bits. So if we want to divide by 16, we need to drop the 4 least significant bits. That happens right here. These 2 lines. This is where we're dividing the column and row by 16. This tick left is a VHDL attribute. Just makes it so you don't need to know exactly the number. You can just do tick left. Kind of convenient. Makes your code a little bit more portable. If you wanted to multiply by 16, you can just concatenate 4 bits onto the bottom of this. So that's really handy. If you want to divide by any number that's not a base 2 number, if you wanted to divide something by 3, that gets a lot harder to do, and there are ways to do it, but that's for a different project. In general, though, multiplying and dividing is not super straightforward inside of an FPGA unless you use one of those magic numbers. Okay, so the very first thing, we're generating the column and row counters, which basically tell you where you are in the game board. Okay, moving down to the Pong paddle control. There are two Pong paddle control modules, one for player 1, one for player 2, and the only difference between the two is the player paddle position in X. So X is going to be fixed for the paddles, meaning X is the column. The column is going to be fixed, so the column location for player 1 is going to be, it's in the package file. We're going to open the package file and figure out where it is. The column location for player 2 is set here as well. And the input to the Pong paddle control is the divided version of the column counter, which is in the 40 by 30 game board space. The paddle up is the debounced paddle up, debounced paddle down, and then the output of Pong paddle control is really just this draw paddle signal, which says at this particular column and row, draw the paddle here. We also do need to pass out this paddle Y position, and this gets used, I'll show you this gets used in this module further down. Player 2, same exact thing. We also have the ball control here. When the game is active, we're going to be drawing the ball, and it's basically the same thing where we're drawing the ball. It keeps track of where the ball is located in X and Y, and it says that this, if this draw ball signal is high, then at this particular column and row position, draw the ball. And we also need to pass the ball position in X and Y out to this module. I created some intermediary signals for P1 and P2 just to keep track of where the bottom and the top is. I think these are both unsigned. So the bottom is at the output, the Y from player 1. This is the output of this paddle control module. That's the bottom of the paddle. The top of the paddle is going to be the bottom plus the paddle height. Okay, I'll show you where this gets used. Down here. In the state machine for controlling the state of the game. So we're in idle until game start happens, and that's when the a byte gets received over the UART. And then we sit and we go through running until somebody scores. So we're checking to see here if player 1 scores, if player 1 gets scored on by player 2, that's this. If player 2 scores on player 1, that's this condition here. Otherwise, we're just looping in this state every single clock cycle. The way that player 2 scores on player 1 is if the ball position in X, which is the output of the ball control module, is equal to 0. If the ball position in X is ever equal to 0, and then we check to see that the paddle position is, basically this is checking to see that the paddle is not there. If the paddle is not at the position where the ball is, then in Y, then we know that the paddle hasn't gotten to where the ball is, so therefore the player 1 is going to be scored on by player 2. So this is checking the ball position in Y is going to be less than the paddle position bottom, or the ball position in Y is greater than the paddle position top. Then we know that the ball is not being hit by the paddle at any given time, so player 2 scores. And it's the opposite for it's the same exact thing actually for player 2, except the only thing we're checking differently is the ball position in X is equal to game width minus 1. So it's at the very last pixel, the very last column on the game. And if that happens, player 1 wins. And we have a little score counter here that just increments when player 1 increments a score. When it gets to the end, score limit, which I think was 9, we reset the game back to 0. Okay, and let's see. This is going to be saying that the game is active when we're in the running state, and then we're going to be drawing this is the OR gate that we showed previously. We're drawing anything, which is an OR of any of the things that we could be drawing. In this case, we could be drawing the ball, or we could be drawing paddle 1, or we could be drawing paddle 2. So we just OR all three of these together, and we know that we should be drawing any one of these three things when any one of them is high. So down here, red, green, and blue video gets set to 1, others to 1, when draw any is equal to 1, otherwise others to 0. So when you set red, green, and blue to 1, all of them to 1, then what that does is it turns them white. So if you wanted like everything to be red only, no blue, no green, you could do that. That would draw everything in red. But I chose white. White's the traditional color, but you can play with the colors here to see what you can draw. So you could draw like the paddles in one color and the ball in a different color, for example. Fun stuff like that. Alright, that's it for the Pong top. I'm going to go into the paddle control next. Oh no, I'm going to do the package file real quick. Package file. Pong package is, this is what it looks like. And here, all I did was set up some constants. Oh, and some component definitions as well. You can set up component definitions if you would like to. But I just set up the game width 40 by 30. We're playing up to 9. The paddle height in board game units is 6. Paddle speed, I set it so that the paddle only gets updated once every 50 milliseconds. I'll talk about that in a second. Where the paddle is located for player 1, where it's located for player 2. Okay, let's go to the paddle control here. Try to speed this up. Paddle control. We're keeping column index, row index. This is something I sometimes do. This signal here is standard logic vector 5 down to 0, but it's kind of a pain to like try to relate that to numbers. So I created this intermediary signal called call index, which is just the integer version of that standard logic vector. Integers are just easier for me to think about, so when you deal with this, you can actually, it keeps your conversions down to a minimum. VHDL is very strongly typed, so you got to make sure you're comparing the right types. So we're only going to be enabling the paddle counter when either the paddle is moving up or down, but not both. So we put an XOR gate in there for that. And down in this main process here, this is our clocked process. If the paddle count is being enabled, so if the paddle is being held, then we're just going to increment a counter. It's going to count up to paddle speed. When it gets to paddle speed, then we're going to set it back to 0. So if paddle speed's low, this is going to be looping around pretty quickly, and that's going to actually move the paddle around the game board a lot quicker. If we didn't have this here, then the paddle, every single time this came through, it would move the paddle one unit for every single clock cycle. The paddle would just move around like crazy. So you can only update the paddle ever so often. So that's what this loop is making sure that it's doing. So we limit the update of the paddle position only when the paddle count is equal to the paddle speed. So if we are moving, if the button is being held to move up, and we're at that paddle speed index limit, then we just want to make sure that we're not at the top. If we're not at the top, then we subtract 1 from the position in Y. Otherwise, if the button is being held down and we are at that limit there, then we can update the paddle position. We want to check that it's not at the bottom, and if it's not at the bottom, then we add 1 to the paddle position in Y. And where we draw the paddle, we're going to be drawing the paddle we got to check for row and column index. This is where we're actually looking to see where we are in the frame versus where the paddle is in the frame. So the paddle is located at player, this is from the input generic, that's where it's located in column. So if it's located in the right column, as we're being currently drawn, call index is the one we're currently drawing, then we know, okay, we're in the right column. Now we need to check rows. So we need to make sure that the row index is greater than or equal to the bottom of the paddle, and the row index is less than the top of the paddle. And if that's true, then we're going to be drawing the paddle. Otherwise, paddle ain't there. That gets sent to an output, and then we need this. This was used in the higher level module. Did I discuss that? Why that was used? That's for scoring. Yeah, I did discuss that. If the paddle is in the same position as the ball, then it bounces off the paddle and goes the other direction. Okay, Pong, ball control, basically the same idea. Call index, row index. The only thing different about the ball is the ball moves in X and Y, so you need to know where it was previously to keep track of which direction it's moving in. So when the game starts, when the game is not active, we're going to put the ball in the middle of the screen, game width over 2, game height over 2. And then we're going to set the previous position to something where it's moving in some direction. It can either be moving up and to the right, up and to the left, down and to the right, down and to the left. Those are the positions that it can be moving. So you can set the movement of the ball when the game starts by changing these signs here. Fun. And then we have this ball speed. So the ball speed is a constant that's set in the package file. You can change the speed of the ball if you like. And then we're controlling the ball in X and Y, and I did it separately, but it's the same concept for both. So first of all, check to make sure that only update the ball when the ball speed index is hit. Register the previous value of the ball to know which direction it's moving. And then check to see if the ball is moving to the right, keep it moving to the right, but check that we're not at the wall, in which case it's going to bounce back. That's what this is doing. If the ball is moving to the left, we're going to keep it moving to the left, check for the wall impact. That's X, and we treat X separately from Y. So that's X, this is Y, same exact idea. And all we need to do is draw the ball when the current column that we're on is equal to the ball's position in X, and the current row that we're on is equal to the ball's position in Y. If that's true, that's where the ball is. Otherwise, draw the ball to 0. That's it. And we pass the ball's position in X and Y out of this module. So I believe that's it for Pong. We did the package. Yeah, that's it. So let's go ahead, program up the Go board, and take a look at Pong. All right, the Go board has been programmed with the code. I have cracked open a COM port here. Let's see. So when I hit something, what does it do? Oh, it starts the ball moving. So the ball moves down and to the left when I hit key on the keyboard. There it goes. That's working correctly. We can check to see that the paddles are moving. So there goes one of the paddles. It's about six ball heights high. There goes the other one. Cool. Now let's see if I can hold the phone and play the game at the same time. This is going to be hard. There we go. Oh, okay, I hit and I lost. I lost against myself. But there we go. Pong is working. Well, boy, this is sad. After many, many hours of tutorials, things are at an end. I really hope you've enjoyed this so far. Definitely recommend the Go board to anybody you think might get some value out of it. And thank you. Thank you so much for your support. If you were part of the initial Kickstarter, thanks very much. I just appreciate everybody so much. So again, thanks, and continue your FPGA experience. I hope it's fun for you guys. Bye.